Greetings everyone, this is Professor Roman. Welcome back to my lecture series on transition to advanced mathematics. Last time we discussed the fact that it was in the very late 1800s, early 1900s, that mathematicians tried to place mathematics on a solid foundation. But that in 1901, Bertrand Russell discovered his paradox, and that caused quite a stir among mathematicians at the time. We discussed very briefly how one might avoid the Russell paradox by introducing the notion of classes, but in 1908, the mathematician Ernst Zermelo decided that the situation surrounding the paradoxes in set theory, and there are others besides the Russell's paradox, required that set theory be placed on some solid axiomatic foundation. And he attempted to construct axioms that would do so. But in a 1921 letter to Zermelo, the mathematician Abraham Frankel pointed out that there were some problems. Zermelo's theory was incapable of establishing the existence of certain important sets, and so it needed some tweaking. We don't know if that was Zermelo's words or not, but he collaborated, the two, Zermelo and Frankel, collaborated together along with a third mathematician whose name was Skolem. And during the years from about 1908 to 1925, the so-called Zermelo-Frankel axioms, or what we usually say as ZF axioms, were developed. And these axioms addressed the following critical questions. Do any specific sets exist? We need, it's not enough just to say, okay, we're going to start with the notion of a set. We need some more specifics. We need to say, yes, there is at least one set, and here's what its properties are. The second issue, how can we tell when two sets are the same? Third issue, how can we make new sets from existing sets so we can get the ball rolling? In total, there are 9 ZF axioms. And it's important to understand that as axioms, these statements have to be accepted without proof. You can't prove them. They are at the fundamental foundations of mathematics. The notions of set and element of set and the ZF axioms to allow us to work with sets. 2 of the ZF axioms say that sets actually exist. One, called the axiom of the empty set, says there is a set with no elements, called the empty set or the null set. Perfectly reasonable. Axioms should seem reasonable. If they don't seem reasonable, then either there's something about the axiom we need to think about further, or there's something about the way our intuition is working that needs resolving. Axiom of infinity, there is an infinite set, and we will have to hold off on what exactly that means until we have appropriate tools for dealing with it. There's one axiom that describes the equality of sets. It says that 2 sets are equal if and only if they have the same elements. Now these are informal versions of the axioms. If we'll get to formal versions later, they're going to look a lot different. So this is all informal stuff. What we're doing here is giving you a sense of what these axioms do. This is not precise enough to actually work with the axioms. Several axioms describe how to make new sets from old sets. The axiom of union says that if you have two sets S and T, their union is also a set. The axiom of pairs says that if you take two sets, you can put them together into another set that has the two sets, S and T, as its only elements. This is not an ordered pair, it's just a pair. Pair meaning a set with two elements. Axiom of Power Set says that if you have a set S, then if you can collect all of the subsets of S together into a new set. It is called the power set of S, and we'll denote it by script P of S. The axiom of separation describes how to extract elements from a given set to create another set. In other words, a subset of the original set. We separate out some elements. It seems intuitively clear that if you have a set, you ought to be able to grab a few elements and put them into another set. But we need an axiom here. The axiom of replacement describes how to use one set S to construct another set X by choosing certain elements from a third set. And that's going to sound very vague right now, and that's fine. You don't need to memorize these axioms. I'm just trying to give you a sense of what Zermelo and Frankel were all about in the early 1900s. There is a ninth axiom called the Axiom of Regularity. This is kind of a technical axiom to avoid certain unpleasant consequences. One of the things the Axiom of Regularity implies is that no set can be an element of itself, which we should find intuitively pleasing, because that seems too weird that a set could be an element of itself. Using these 9 axioms of set theory and a sound logical framework in which to work, various mathematical theories known as branches of mathematics have been developed. It might seem like not much could come from the undefined notions of set and elements and just these simple 9 axioms. But evidently, that's not true. The American Mathematical Society has divided the subject of mathematics into 67 major categories with 6,197 subcategories. In fact, the list of subcategories is 97 pages long. So mathematics is huge. Excuse me while I have a sip. My herbal tea. Here's some other kind of staggering statistics. There have been over 3.5 million research papers published in mathematics. A research paper is a paper that contains new ideas in mathematics. And these papers have been authored by over 800,000 different authors. There are over 1,800 different journals devoted to publishing new mathematics. And currently, some 125,000 new papers containing more or less new mathematics are written every year. Every once in a while, someone will ask me when they hear I'm a mathematician, how can you be a mathematician? Isn't all of mathematics known? And after I have a chance to catch my breath, I try to explain that that's not the case as gently as I can. I guess you already know that to be the case, because you know the Collapse Conjecture is not known. The various branches of mathematics can be thought of as the study of sets with structure. If someone asked me what mathematics was, and I only had a few words, a sentence to respond, I would say it's the study of sets that have various structures applied to them. Here are some examples. This list is a gross oversimplification, but it makes the point, I think. Mathematical logic is the study of sets with a deductive structure. That's a structure that allows us to define the fundamental notions of proof and theorem in particular. And of course that lies at the very foundations of mathematics, because as we've discussed, you can't do mathematics unless you can reason logically. Set theory, as we've said, is the study of arbitrary sets and also lies at the very foundations of mathematics. Abstract algebra is the study of sets with an algebraic or arithmetic structure, usually referred to as addition or multiplication. Number theory is the study of the integers, which is a set with an incredibly rich mathematical structure. It's not as simple as it may seem. Well, the Collapse Conjecture shows all by itself that there's something going on in the integers that's beyond our ability to comprehend at this time. Order and lattice theory, as we've discussed briefly, is the study of sets with an order structure, so we can say what it means to say that one mathematical object is larger than another. This area of mathematics touches upon virtually all other areas. Point set topology is the study of sets with a continuity structure. So if you've taken calculus, you're familiar with continuity. The fundamental concepts of point set topology are continuity, compactness, and connectedness. Mathematical analysis is divided into two areas: real analysis and complex analysis. And those are the study of either Rn or Cn. Rn is called n-dimensional Euclidean space. R2 you should be familiar with. It's the plane, Euclidean plane. This is the complex version, Cn, of Rn. And analysis is the study of one or the other of these with a differentiability structure. So this axiomatizes the notion of smoothness, which you would have studied in calculus. Continuity with no sharp corners. That's what it means to be smooth. It has to be continuous and have no sharp turns, sharp corners. Real analysis is the most direct extension of calculus to higher dimensions. Differential geometry is the study of smoothness, again, but in a setting more general than that of Rn or Cn. In a setting of sets that are locally, but not in general globally, like Rn or Cn. For example, think about the surface of a sphere. And suppose it was a huge sphere and you were located on the surface. You couldn't look up, you couldn't look down, all you could see is your surface. That's all there was. To you, in a small area around you, in a neighborhood around you, it would look like you were in a plane. It might be a, somewhat bent plane, if you could determine that or not, doesn't matter, but it looks like a plane. For all intents and purposes, it is a plane locally. You can't tell that you're not really in a plane, warped or otherwise, until you make a complete circumference of the circle. You head in one direction, eventually you come back to where you started from. And when that happens, you say, aha, this ain't a plane. Because you can't do that in a plane. So you have to have the global perspective to tell you're not in a plane. These things that are locally like Rn or Cn, but not necessarily globally like Rn or Cn, are called manifolds. And differential geometry is the study of manifolds. Probability is the study of sets with a likelihood structure. This area of mathematics began with the desire to predict the future of games of chance. People wanted to predict the future for obvious reasons, but it has now an incredibly wide range of applications in other areas of mathematics and the sciences. Quantum mechanics, for example. Measure theory is the study of sets with a structure that is imposed by what we call a general measure. And that's a generalization of the notions of length, area, and volume. Measure theory and real analysis are tied in together quite considerably. Euclidean, affine, and projective geometry. These are the study of sets with a structure, an axiom structure, that comes from the ideas of angle, parallelism, and other things, invariance under transformations and that sort of thing. So we have a list here, a short list from among the 67 major categories. This is just a handful, but it gives you a sense that we're talking here about sets with some kind of structure. And many of these areas, of course, overlap. And to be successful at studying one area, one often has to have considerable competence in related areas. Okay. Now, it might be fair to say that there are four fundamental concepts in the study of mathematics. And these are axiom, definition, theorem, and proof. An axiom is a statement, as we've discussed, that is accepted without proof. Most likely because it can't be proved, as is the case with the ZF axioms. A definition is simply a statement describing the precise meaning, and I mean precise, of a mathematical term. One of the greatest challenges facing students in my almost 50 years of teaching university mathematics, actually 51 years I've taught. I taught my first math class in 1970 at a university. One of the most difficult challenges facing students one that students do not like to accept, is that all definitions must be learned immediately upon their introduction. Definitions are the vocabulary. If you want to learn the French language, you've got to study the vocabulary. You got to know the vocabulary. You got to learn it immediately. Same thing with mathematics. A theorem is a statement of fact in mathematics, at least once it has been proven. Theorems always are supposed to have proofs. And once it has been proven, then it becomes a statement of fact. Theorems are the tools by which we build new mathematics from existing mathematics. All theorems also need to be learned immediately upon their introduction, or at least you need to have a pretty good idea so that you can say to yourself, gee, I think yesterday I saw a theorem about this. I can't remember the exact wording. I can look it up. But if you just read a theorem and then dismiss it from your mind, you're going to have problems, because that theorem probably will be needed later. As I mentioned before, mathematics requires precision. Any gap in precision can lead to disaster. The problem is we all have a tendency to rely on our intuition. We look at something and we say, yeah, that looks true. I'm okay with that. That is dangerous in mathematics. And I'll give you some examples. Okay? We can't trust our own intuition. Sometimes it's accurate. Hopefully a lot of the time it's accurate. But even great mathematicians have said, I think the following is true. My intuition tells me it's true. I don't have a proof. Turns out later it's not true. Try this one on. There are 365 days in a non-leap year. So if a room contains 366 people, then of course at least 2 people have to have the same birthday. 365 birth dates, 366 people. 2 people have to have, at least 2 have to have the same birthday. That's called the pigeonhole principle, and we'll actually discuss that later in the course. Well, how many people do you think need to be in a room so that the chances are 99.99999% that at least 2 people in the room have the same birthday? So it's not absolute certainty, but it's very close. So would you guess maybe the number is close to 366, maybe even 300 or 250? What does your intuition tell you about what that number should be? Well, the answer is 100 people. If there are 100 people in a room, then there's a 99.99999% chance that 2 of them have the same birthday. Even though there are 365 different birthdays, 100 people is enough. So that's an example where a person's intuition can easily be misleading. If your intuition told you, gee, I think it's probably around 100, that's great. More power to you. Try this one. Do you think it's possible to take a solid sphere of radius 1, cut it into several pieces, and then only by moving the pieces around without stretching, shrinking, or tearing, just move them around, to reassemble the pieces into two spheres of radius 1? Well, I guess most people intuition would say that's absurd, and one might reasonably argue that the volume of a sphere of radius 1 is 4/3 pi, 4/3 pi, is fixed. How can you take a single sphere with volume 4/3 pi and without stretching, shrinking, tearing, just by moving them around rigidly, produce two spheres, both of which have volume 4/3 pi? You've doubled the volume. Well, this you cannot do. Okay. So would that convince you then that this whole process is impossible of making two spheres out of one? If it does, you would be wrong. The so-called Banach-Tarski paradox is a theorem that states that a solid ball of radius 1 can be cut into non-overlapping pieces that can then be rearranged only by moving the pieces around without changing their shape into two balls of radius 1. Now, the reason that the volume argument breaks down and doesn't contradict the Banach-Tarski paradox, I guess one should call it the Banach-Tarski theorem, but nobody does. It's so paradoxical that that name is stuck, is that the pieces required to perform this magic are so porous that they do not have a volume. Remember I mentioned there was a branch of mathematics called measure theory, which generalizes the notion of length, area, and volume. What is part of measure theory is the fact that some sets on the real line, for example, or in the Euclidean plane, are so complex, so porous, if you want, that they cannot be measured. So they don't have a length if it's in the line, they don't have an area if it's in the plane, they don't have a volume if it's in 3 dimensions. These sets are called non-measurable sets. They are very hard to construct. I don't think you would see a non-measurable set unless you went to graduate school in mathematics. I don't think there are any undergraduate courses that cover that. I could be wrong, I don't know. But they do exist. They can be constructed, non-measurable sets, but only by scrupulous attention to precise detail. Can't afford to skip any steps, because if you skip a few steps, you get to the end and it says there's a non-measurable set. You say, well, that doesn't sound right. Maybe there's a mistake. So you've got to have sound, logical, precise reasoning to arrive at a conclusion you can trust, even if your intuition finds it hard to believe. Well, we've discussed the Goldbach conjecture, which is certainly a simple sounding problem with an apparently extremely difficult solution. But the Goldbach conjecture is not the only, it's not alone in this category. So I want to give you a few more examples. Twin primes. A twin prime is a pair of prime numbers that differ by exactly 2. 3 and 5, 5 and 7, 11 and 13, 17, 19, 29, 31, 41, 43. Prime numbers differing by exactly 2. Now, despite the fact that there are infinitely many prime numbers, and this is, by the way, something we will prove later in the book, their distribution does thin out. Prime numbers become rarer the farther we go out into the integers. The same holds true for twin primes then. However, it is unknown whether there are infinitely many twin primes. Current research seems to indicate that there may be infinitely many. High-speed computers have told us that there are roughly 808 billion twin primes below 10 to the 18th. But again, that's not anywhere close to being a proof that there are infinitely many twin primes. So this is another unknown, a simple sounding problem with that nobody knows how to solve. Here's another interesting one called the sofa problem. And there's a picture to go with it. The sofa problem is the problem of determining the rigid two-dimensional shape, this is the blue shape here, of largest area, and finding that area, that can be maneuvered around this corner. So this is a unit width corridor, you might say. You know, the reason it's called the sofa problem is because somebody's trying to get a sofa around the corner in an apartment building or something. And what is the biggest area and what shape does it take that can still get around this corner? Okay. The area is called the sofa constant. The exact value of the sofa constant is unknown. In this figure, this shape here, this is called the Hammersley sofa, and its area is 2.2074 square units. But it's not the largest known object that will go around this corner. All we know at the present is that the sofa constant is between these two numbers. That's the best we can do at present. Now, please understand, as some of you may be saying, well, what do I care about getting a sofa around a corner? And that's reasonable. You may not even care about the sofa problem at all. But I hope you can recognize that it's rather odd. We don't know how big a piece of furniture we can get around the corner here. I mean, that ought to be something that somebody could figure out. And yet, nobody's been able to. So that should be at least recognized as remarkable. Okay. Here's another one, the Collats Conjecture. Start with any positive integer n and construct a sequence of integers by the following two rules. If the current integer, call it k, is even, divided by 2 to get the next integer in the sequence. If the current integer is odd, multiply it by 3 and add 1 to get the next number in the sequence. So here are some examples. 6, cut it in half, 3, odd, multiply by 3 and add 1, get 10. That can be cut in half, 5. This is odd. 3 times 5 is 15, plus 1 is 16. 8, cut it in half, 4, cut it in half, 2, cut it in half, 1. Here's another longer example. you should do this yourself. Start with 7 and work it out. The Collats Conjecture says that no matter what integer n, at least equal to 2, bigger than or equal to 2, that you start with, the sequence will always reach 1 after a finite number of steps, as these two did. In the past 80 years or so, since this was first brought to light, no one has been able to prove or disprove the Collats Conjecture. This is named after Lothar Collats, who introduced the problem in 1937. And it has other names, the 3n+1 conjecture, the hailstone conjecture, and so on. The sequence of integers that are produced by this process is called a hailstone sequence. And the explanation is that because the values usually are subject to multiple descents and ascents, like hailstones in a cloud. I guess that's what hailstones do. I don't know. If you are planning on solving the Collats conjecture, one thing you should know is that as of the year 2017, the conjecture has been verified by computer for all starting values up to 87 times 10 to the 60th, which is merely this number. So start with the next integer after this and try it out. I guess that should give you a hint that some ideas are necessary, not just brute force. It's way beyond, let's check some more and maybe we'll find that something doesn't end up at 1. We're well beyond that point. One final paradox. Can you imagine a container that can be filled with paint right up to the brim, but the paint won't cover the entire inside surface of the container? Seems ridiculous. If a quart of paint is enough to fill a container to the brim, you must have painted the inside surface. Gabriel's horn is formed by taking the graph of the function y equals 1 over x for x bigger than or equal to 1 and revolving it around the x-axis. So this goes on infinitely far, but these points come together because these curves are asymptotic to the x-axis, so they're converging towards the x-axis. Now, if you have taken calculus, you know how to compute the volume of what is called a surface of revolution. This is the formula, it's this integral. It comes out to be pi. So the total volume inside Gabriel's horn is pi cubic units. The surface area is given by this formula. It is infinite. So Gabriel's horn has a finite volume, pi, and so can, well, at least in theory, be filled with pi cubic inches of paint, yet the horn has infinite surface area, so the interior can't be painted with any finite amount of paint.